Hello, this is Captain Chaudhari. In my series of videos on marine astronomical navigation, we were trying to learn the astronomical calculations. So when an angle is 90 degrees or a side is 90 degrees, in case of a spherical triangle, we can do the calculations using Napier's method. And then in addition to this 90 degrees angle or side, we must know any two things in the spherical triangle, and we are able to discover every angle and every side of the spherical triangle. So what is necessary is, in addition to the 90 degrees component, we know two more things. As you know, sides as well as angles, they are measured in terms of angle, right? So let us do one calculation which will demonstrate both the types of Napier calculations. Okay, then let us see that there is this latitude of 40 degrees north, and then we have the sun's declination as 15 degrees north. It is required to find out, number one, what is the duration of daylight, and number two, the altitude when the sun's sight is most suitable for a longitude by Cron calculation. So there is this long by Cron method of finding out, sometimes it is called longitude method of finding out the position line. Well, we've got nothing to do right now with the long by Cron calculation, because I'll be doing it separately. At the moment, let us understand that long by Cron sight is actually used generally out at sea to do the running fix. Running fix is done with the noon sight, and in the noon sight, you know, the position line is east-west, because the sun would be observed in true north or true south direction, so position line is east-west. And because the position line at the time of meridian passage is east-west, a long by Cron would best be at the moment when the position line is north-south, and that would happen when the sun is exactly bearing 90 or 270, right? So in other words, in this question it is asked, like, what would be the altitude of sun when the sun is bearing exactly 090, or when the sun is crossing observer's prime vertical. So diagram wise, it would be like this. We are talking about an observer's rational horizon diagram. This is west-east, the north-south, and I divide this part into 9 segments, and because the latitude is 40 degrees north, 10, 20, 30, 40, the equinoctial would be like this, and by the same amount the north celestial pole would be here. This is observer's zenith, and this is the equinoctial, WQE. Now we have the declination of the sun as 15 degrees north. That means 15 degrees from equinoctial, north of equinoctial. So apparent daily path would be something like this. The sun, this is called D dash D, and the sun is rising over here. Sun would rise over here, right? And at this moment, the sun is going to bear 090, or the sun is going to cross observer's prime vertical, and in this case, observer's prime vertical is WZE. So it is required to find out first what is the duration of daylight, right? And to find out what is the duration of daylight, we need to capture this angle. We need to capture this angle. So the idea of doing this numerical is basically to understand the Napier's calculations. Napier's calculation can be done at the time of theoretical rising of the body or setting of the body. The zenith distance, the true zenith distance of the body is 90 degrees. And in this triangle PZX, we would first write down whatever is 90, we write down on top. Then I told you, without looking at the PZX triangle, are you able to say who will be the neighbor of side zx? The neighbor of side is angles. So the neighbors of side zx would be one angle is z and other angle x on the other side. So we'll write down z and x as the neighbor of zx. Now who's the neighbor of z? Neighbor of z would be the two sides which have z in them. One is zx and other one should be pz. Similarly, who are the neighbors of x? One is zx and other one should be px. The only component that is remaining therefore is p, right? And in the Napier's diagram, we make a diagram like this and we write down 90 minus in this particular section. That means whenever you are using any of these parts, you cannot use those parts directly, you have to use 90 minus. Now, whenever we do Napiers and the side is 90, we have to remember one a special procedure or rule that whenever a side is 90 and on the right hand side both the parts are angles or both the parts are sides, you introduce a negative sign. So let us see, in this particular question we are given latitude and declination, and you know pz is always 90 minus latitude and px is 90 plus minus declination. So in this case you can see that the px is less than 90 degrees because the distance to the equinoctial is 90. So this is less than 90. So we would say px is 90 minus d. And what we need to find out for the duration of daylight is we have to capture this angle p. This angle p is the angle that is traced from sunrise to meridian passage, right? So we need to find out this angle p. So when all the three parts are together, we have the first rule of Napier's, that is sine of middle part 90 minus p, because we are selecting the parts from these lower three, we have to write 90 minus. Sine of 90 minus p is equal to tan 90 minus pz tan 90 minus px. But because a side was 90, so side is 90, so if on the right hand side we have both the parts as sides or both the parts are angle, then we need to introduce a negative sign. And therefore the right hand side can be written as minus 1, which is introduced. Tan 90 minus pz is 1 upon tan pz. Tan 90 minus px is 1 upon tan px. And this is cos of p is equal to minus 1 upon tan 50, 90 minus 40 is 50, tan 75 degrees. So it is right hand side is equal to minus 1 divided by tan. I get an angle of 102.9 and so almost 103 degrees. So P is equal to 103 degrees. So if this angle is 103 degrees, by the time the sun sets, the angle that would be traced will be 103 plus 103, that is 206 degrees. And 206 degrees divided by 15 degrees, that would give me, in terms of hours and minutes, it would be 13 hours 43 minutes and 56 seconds. So the duration of daylight is 13 hours 43 minutes and 56 seconds. So this is how we have used Napier's rule when the side was 90, and you have understood when do we introduce a negative sign. If on the right hand side one part was side and other part was angle, we wouldn't have introduced negative sign. At this moment I would also want to tell you the cosine and tangent that we use, the cosine and tangent function that we use are good indicators of the quadrant. If cosine is negative, because you see in the spherical triangle either you have an angle less than 90 or more than 90, you can't have an angle more than 180. So now the choice is between the first quadrant and the second quadrant. Please understand, when cosine and tangent are negative, they indicate that the angle is in second quadrant. So we have seen this angle P that we got was 103 degrees. Double of that angle divided by 15 gives me 13 hours, 43 minutes and 56 seconds. Now we are going to work this triangle. So you can see the internal angle Z would be 90 then. So we have the rules. We may remember a few rules. They can be considered as, the golden rules, like here. Number one, when a body crossing observer's prime vertical, angle Z is equal to 90 degrees. That is number one. Number two, the conditions for body to cross observer's prime vertical is number one, latitude and declination should be of same name, and number two, declination is smaller than or equal to latitude. So these are the two conditions which must be satisfied in case you want the body to cross observer's prime vertical. So after understanding these conditions, let us make the Napier triangle. Napier triangle is made by putting the part that is 90 right on top. So Z is equal to 90. Who are the neighbors of Z? Without looking at the PZX triangle, you should be able to say PZ and ZX. Who are the neighbors of PZ? Z and P. Neighbors of ZX, Z and X, and remaining is PX. Now we know the latitude, so we know PZ. We know the declination, so we know Px. It is required to find out the Zx. So now the equation that we are going to write is, because the parts are scattered, right? They are not grouped together. So I will use the second rule, that is sine of 90 minus Px is equal to cos Pz cos Zx. Now the point to be noted is here, the angle is 90, Z is 90. So there is no question that we introduce a negative sign. So we will go as it is. So you can see cos Zx would be cos Px upon cos Pz, that is cos 75 divided by cos 50. This gives Zx as 66.26 degrees, and therefore distance from here to here as 23.74 degrees.